Hi, everyone. Thank you so much for joining us today for the webinar. We're super excited to have you here and to talk about our 2020-21 machine learning practitioner survey, and of course, spend some time with Stanley here from Ancestry. So before we kick it off, just to give you a quick background about myself and Stanley. Stanley Fujimoto is a senior data scientist at Ancestry, the largest for-profit genealogy company in the world, which operates a network of historical records and genetic genealogy website. He has used traditional computer vision, NLP, and deep learning approaches for text classification, clustering, fact extraction, and handwriting recognition. I'm Gideon Mendes. I'm the CEO and co-founder of Comet. I started my career as a software engineer about 16 years ago and shifted to working on machine learning about 9 years ago, both in academia, startups, and then my last role before Comet, I was working on hate speech detection on YouTube comments at Google. So a lot of language modeling and NLP. Unfortunately, that was the pre-transformer days, but Stanley, I'm sure we're going to talk more about that today. But before we kick it off, Stanley, and hear more about what you're working on, I want to spend just a few minutes to talk about the survey that I mentioned before. So a few months ago, Comet ran a survey. We spoke to about 500 practitioners. So these are machine learning practitioners, data scientists who build models on a weekly and daily basis from various industries, working in various use cases, different types of model, different types of problems. And we've definitely learned a lot of really interesting things, and we'd like to share some of these results with you today. I'll only cover a small portion of it, but if you're interested in digging in, the full survey results are available in the webinar. If you look on the sidebar, there should be like a handouts tab, and you'll be able to have full access to it. So let's kick it off. So one of the things we're seeing, and I think for a lot of practitioners, that's not a huge surprise, is there's too much friction, unfortunately not enough ML, right? So one of the things we've heard is almost 60% of the data scientists and practitioners out there use manual tools to track machine learning experiments. And by manual, we're typically talking about notes and spreadsheets, which is better than trying to remember everything you did. But unfortunately, as a lot of you probably know, with everything that comes to building a model, hyperparameters, configuration, data sets, orchestrations, it's very hard to keep track of everything manually, not alone try to reproduce it later. The second part, which is closely related, is almost 70% of the people surveyed share that they abandoned about 40 to 80% of their experiments in the past year. So these are experiments that could have potentially go somewhere and work, but because of challenges with infrastructure, challenges with tracking, potential bugs in the process, they had to throw them away. And of course, not only that leads to wasted time, but in many cases also wasted GPU hours. Additionally, as you know, we keep hearing, and obviously I think the industry have improved on this side of things significantly. There's a huge lag between when a model's finished training and the data science and the machine learning team feels it's ready to go to production to when it actually happens. So 43% responded that it takes about 3 months, and 47% said it takes longer, so 4 to 6 months. And a lot of people talk about how painful that handoff is when you have your model binary and maybe some basic Python code that calls the predict function, how hard it is to get it to the team or the person that has to put it behind an API and actually in production, and everything that goes with that. The third point, and the last one I'll cover from the survey today, is we are seeing a lot of companies out there understand that this is something worth investing in. So as you can see, 63% of teams reported they're planning and increasing their machine learning budget, and this is excluding headcount budget. This is just for platform and tooling. But yet today, if you look at the budgets, about 88% of them said that their full budget for platform and tooling is less than $75,000 a year. There's another result that you'll see in the handout if you look that's missing here, but most of these organizations have between 4 to 6 teams, and the average team is about 5 people. So if you factor $75,000 for quite a meaningful amount of people, that's actually shows that there's like a very meaningful opportunity to make an impact here and allow you and your team to focus on what you're good at and build models, focus on the science, try different things, and not be boggled by like infrastructure issues, tracking issues, deployment issues, all these things that are super critical, but from our experience as a data scientist are kind of like necessarily evil. There are like very good news here. So, you know, companies like Netflix and Uber have pioneered solutions to some of these challenges with really excellent results. Some of them, like, you know, Netflix made some of their tooling open source. Uber has a platform that's called Michelangelo, which isn't open source, but they are using Comet on top of it to manage all the experimentations. And on top of like the actual tools, a lot of the lessons that they've learned is documented in their engineering blogs, you know, conference sessions, and with the growing ecosystem of tools, it makes it much easier for machine learning practitioners to build, you know, machine learning models better and faster. Back in the day, I don't know if Stanley, if you were training deep learning models at the time, was when I started, I was using Theano, which even getting, you know, a simple logic that isn't like very trivial was really painful. And now these days with like PyTorch, TensorFlow, and some of like the high level libraries like Keras and PyTorch Lightning make the task that we've been kind of dealing with back then like trivial. So we're very excited to see kind of the ecosystem move forward and continue to improve on that. That said, like one of the things that's important with the growing ecosystem, and you know, a lot of teams out there are trying to figure out, okay, what should we buy? What should we build? What open source solution should we use? How do we even go about this, right? Like, there's definitely a lot of noise in the MLOps ecosystem, and we hear from a lot of customers and prospects that they sometimes find it hard to understand who's doing what and what's important. So we collected a few of the lessons that we've heard from our customers that work for them, and just want to cover those points, which some of them might not seem apparent on first look, but are absolutely critical to make this successful. So the first thing is around integration and customizability. The MLOps stack is going to continue to grow and improve. It could be that in the future you want to introduce a new tool. It could be that your workflow is going to change, and you're really looking for tools that are highly customizable to your workflow. So if today you're working with PyTorch and a specific type of data, that could look very different, and you want to have the flexibility and kind of this future-proof feature set that allows you to continue to iterate, to update things on your side without finding that the product, the tool, the platform that you bought is holding you back. The second thing here is scalability. You know, I think a lot of people are aware of some of the challenges in like serving in scale, but it's not just on the serving side. So even things like tracking, orchestration are really hard to do in scale. And if you're testing a product with a couple of workflows, maybe a notebook, it's really hard to understand that. So you're looking for something that really can scale. And it's interesting here, scale doesn't mean you have to have hundreds of data scientists working on it. It's obviously use case dependent, but we've seen some of our customers where there are small teams that are really pushing the envelope and training, you know, hundreds of models, and some of the solutions that I've used before Comet unfortunately couldn't kind of meet that scale. The last thing when you're thinking about this is, how does this fit your overall MLOps strategy, or like how do you plan on solving the complete machine learning lifecycle? So, you know, we're huge believers that you want to have the flexibility to bring in different tools, connect them, and build a stack that works well for you. So that's why customizability is super important. But it's also important to think about the entire workflow. So not just solve a specific problem today, because when you get to deployment, when you get to monitoring, when you get to retraining, you might find that whatever you put in place in the first place doesn't cut it. So thinking about the three key points, super critical in order to be successful with bringing in an MLOps tool, open source, vendor, commercial, it doesn't matter. These things kind of come into play in both cases. All right, so thank you so much for listening to me. And we want to switch gears now, and we have an amazing guest, Stanley, here. So definitely want to spend some time with you. So I have some questions here, just high level to kind of set the discussion. But before we jump in, Stanley, maybe if you can tell us a little bit about yourself and maybe one of the recent projects, machine learning projects you've been working on.
Yeah, thanks for having me. So I've been at Ancestry since 2019. I guess I interned and then I started full time the year following. So I've been at Ancestry for a little bit. It's been a really great experience. I've seen a lot of things where the data science org is kind of new at Ancestry. So it started about 5 years ago, and so there have been a lot of different phases that we've been in and a lot of things that we've experienced that have been interesting experiences. One of the really cool projects that we've been working on recently is the U.S. 1950 census was released earlier this month, and so the census is, Ancestry as a genealogical company, they're very interested in the U.S. Census. Where I don't know if any of you participated in the census. I think it was 2 years ago or something like that, but I guess it was canceled or postponed because of the pandemic. But yeah, they gather all this information about all of the people that live in the United States, and so you can find your ancestors in it. Like I've found my grandparents in it, and it's this very weird feeling of seeing this, or feeling this connection to people in the past. And so the National Archives, they're the ones that digitize all of the census forms. So they're just these big, really big images of scanned machine printed forms that a person would fill out with a pen. And then the problem is that none of those images are searchable. So we needed a way to actually index them. And so we used a bunch of different methods, some traditional computer vision methods, but mostly relying on deep learning techniques to, we used deep correspondence matching as a way to identify where on the forms all of the information was. And then we used a bunch of different architectures in our handwriting recognition. So using just like LSTMs, transformers, and like a full encoder decoder transformer architecture to be able to actually read the handwriting recognition. And so this was a really big and risky project for us because there's competition in the family history space to be able to publish these records as fast as possible. And so the situation that we had was data science, you all have one shot to process all of this stuff. You won't be able to see any of the data beforehand, so you're gonna have to build all your models based off of previous censuses, and you won't know exactly what it's going to look like, but you have one shot to process it, and if it doesn't work out, you don't get another chance. We're just gonna send it to vendors to transcribe them by hand.
No
and
pressure.
so this was a project. What was that?
Yeah, no pressure, I said.
Yeah, so it's funny because the data got released midnight, April 1st in like Washington, DC time. And so we were all in the office Thursday night waiting for all the data to release. And we were doing hyperparameter tuning as we were seeing the data come in. And so it was, they release the census data every 10 years. And so I think every 10 years is about the right cadence to have that kind of stress in your life. But yeah, it was a really fun project. We developed a lot of really cool models that had really high performance. We're seeing some really great feedback on it. Yeah, Comet played a huge role in us being able to be successful. It was, like I said, it was a very risky project for us. And so I think that there's been a bit of a paradigm shift within our organization as to the types of things that we need to focus on. I think so for myself, coming from an academic background, and a lot of people that I've worked with as well, we're used to reading like papers and reading about new architectures on archive, and like seeing all these papers that come out so fast you can't even read them all, and getting really excited about that stuff. And so I guess like to this first question, what are some of the challenges we face? Like it's not, so I was actually talking to a friend in my neighborhood. So he works as a data scientist somewhere, and I asked him if he felt a lot of pressure to like keep up on all the latest methodologies and stuff. And he said, what he said is, no, we have enough math. What we're lacking is execution. And so I thought that was very interesting. And I mean, it really is the execution where, like in a paper, you can have, your results can be really cool. And some of the bad results you can still show, and people will be forgiving of it because they're like, oh man, this is such a cool architecture. But when we show our business partners bad results, or the bad results get shown to the customers, they don't think about how innovative the model was. They just say, they're putting money on the line, they're paying for a service, they don't care how cool the model is. They want to see good results. And a lot of those good results come from infrastructure, from being able to collaborate well with your partners, from really being able to dig into your work and your outputs and have some sort of level of service that you can guarantee. And that's not something often focused on in academic papers, and it's not something you find in some random GitHub repo that has research grade code in it.
Yeah, I mean, there's definitely a huge gap from that perspective between academia and industry, and I think there's a lot of things kind of feeding each other, which is great. But super excited. I want to dive in. I think you mentioned a few things, but just for people listening who are practitioners, and we talked a little bit yesterday about the model, the problem you've been working on. So want to dig in a little bit deeper into that. So you mentioned the census data is essentially images of scanned documents, but I think you said it was microfilm, which is I don't know how many data scientists could say they worked on microfilm data, but that's super exciting. And if I understand correctly, the task is you're getting this form and you're trying to understand, essentially extract all the content from it, but in a structured way, right? So
Right.
what I'm curious about, like you mentioned, like you didn't know what the form would look like beforehand. What was the structure in any way? How did you, and you guys were planning and kind of getting ready for that data set to drop. How did you go ahead and before that and prepare? So what was the things you could have done earlier that hopefully paid off when you went into training?
Yeah, so the model we use, so we just used an off-the-shelf model. We didn't want to, we really were hesitant to like fine tune any model to extract information from the pages, like fine tuned on the 1940 census or some previous forms, because we just had no idea what the 1950 census was going to look like. And so we actually built this really cool architecture to where we could interact with our partner teams and they could provide inputs to the model as well. And so usually in the past, when we've built models, like we train some deep learning model and it's this big black box, and our partners assume that we've baked in all of the domain knowledge that's necessary. And usually we don't understand family history and genealogical stuff as well as they do. And I mean, like when I hear family history, like it's not something that like inspires like a lot of excitement in me. But like being at Ancestry, I've seen a lot of really cool stuff, and it's the types of problems that we're facing. Like I'm amazed at the cutting edge stuff that we're doing. So there are just so many problems, so many like computer vision problems that we're facing. And so specifically with the 1950 census, we wanted it so that our partners with domain knowledge could feed in information to the model so that it could do better at production time. And so doing this using a deep correspondence framework versus like an object detection or semantic segmentation approach, we didn't have to fine tune a model. We just needed good like exemplar images of the actual census forms, and then some additional like meta information like specific landmarks that are telling of a specific so in the 1950 census, there are slight variations in certain census forms, and the variations are important because they keep a bunch of supplemental information at the bottom of the page. And the way that you link a person from the bottom of the page to the top of the page is by doing this fine-grained recognition of different layouts of the forms, which otherwise look very, very similar. And so again, it was something that we don't know a lot, and it's like I don't know much about the 1950 census, but our partners, they know that they're very familiar with these old historical documents, and so by allowing them to as well identify and say like, hey, this is an important landmark within this form or feature, and it's telling of the specific form type we're using. You can use this to differentiate them, and so it was cool too. And so where we used this approach that was very collaborative with our partners, and then like again, Comet is this really big component for us because of the collaboration, especially where we're working with non-data science groups, and they can give us like a config file with marked landmarks, and we can process data through our models, and we can log the images to Comet, and they can just look at them through a web interface. don't do UX stuff. I feel like making a command line interface is something that's very beautiful, but not everyone feels that way. When we print out a confusion matrix in the terminal and show that in the slide presentation, our boss doesn't like that up very much. And then whenever I use like matplotlib, I feel like I don't know what's happening. And then anyways, people told me I should learn ggplot, but I just don't feel like I should learn R at this point in my life. So having a user interface like Comet, like it looks great. Like our partners, when they look at it, it's always very impressive, and it's easier to take like screenshots off of that and throw that into a slide deck, which is a process. That's something that happens way more frequently than I thought would happen in my life, is needing to prepare slide decks to show our results and show how things are actually working to other people. And hundreds of hours of our time, I think, were taken up just making visualizations. And so like dumping images to disk, rsync or SCP them over to our local machine, try to find the text file with the corresponding ground truth, and then what the model predicted, and then like overlay them, and then like space everything out in the slide.
That sounds painful. Yeah.
Yeah, it was all saved by automating it and visualizing it within these infrastructure tools.
Yeah, so curious, I mean, jumping a little bit ahead, I know we talked a little bit about it, but essentially once you make using the deep correspondence method, you kind of detect what field is it in the form, and then you use OCR to extract the actual text from it. And then one of the things you were talking about when we spoke is how to debug this, how to kind of look at the model results, right? Like it's trivial if you're doing something like, maybe object detection or segmentation, that's a little bit easier. But in your case, you have multiple models involved, right? Like I think you mentioned in some cases there were like almost 6 models here, and you're trying to compare and trying to understand. And I think the more interesting point is you're also collaborating with people and partners who are not necessarily data scientists. So you started talking about this, but I'm curious, how did Comet help to do something like this, help solve this problem?
Yeah, so it was a huge collaboration, this 1950s project. So the data science group, we had our own set of engineers that were deploying our models, and then we had another group of engineers from several other other teams that we were integrating with. Excuse me. And so like that Thursday night when we were all processing everything, everyone was heads down and everyone was focusing on making sure their component of the pipeline was working correctly. And so it's like a lot of times, like we'll package up a model and then we'll send it off to somewhere and it's deployed and it's processing stuff, and we don't know what's going on with it. We hope it's doing well, but that's our level of involvement. But there was so much risk involved with this project that we put a lot of emphasis into our monitoring tooling, and so when everything is running through inference, like we didn't have ground truth, so we couldn't check to see how our model's performing in an automated way, but we could like log a bunch of stuff. So we were logging like confidence scores, we were logging visualizations of the predictions that we were having, and so all of that stuff was being dumped out to Comet. And so it was really nice because, well, we didn't have to be like doing some manual process of like pulling our processing logs from S3 and doing all that stuff. All that stuff got automated, and being able to visualize it like in graphs was super helpful. And one of the experiences that was really nice is because we didn't have any ground truth, like it's hard to know what exactly is going to go wrong or why it's going to be weird. But like when you're watching the plots and you kind of have a feeling of how your models work, like you'll start to notice things. And it was actually monitoring the confidence scores that we were plotting. Is we noticed that certain fields within the census weren't performing that well because they looked quite a bit different from what we were expecting. And so we didn't think that the enumerators for the census were going to fill them out that way. And so logging those confidence scores, we saw that these fields, the confidence scores were much lower than other fields. And so we were able to inspect the results, look at, anecdotally look at some of the images that we were visualizing, and then make modifications to our model. And so, we were having these daily stand-ups very early in the morning. And so like the next morning, we show up to this meeting and we say, we noticed a drop in performance, and we have a fix already for it. So we can deploy this model if you give us the go-ahead. And that is a much better position to be in than like a week later, when another team finally has time to go look at the results and say, hey, something was wrong. Do you know what's happening? And so it's much better being able to present the solution because we were monitoring it versus being told something is wrong after the fact, and then not really having a good grasp on what was going on in the situation. That was one of the biggest things that Comet helped us with during that time. And it was really nice, the reporting feature, like our partners could just go in and they could poke around and see what the outputs looked like. And if they had any input, they could give it to us. And so I think that was one of the other things is the collaboration. And we found that it can be helpful even for collaboration with people outside of the data science group.
Awesome. No, thank you. Thank you so much for saying. And it's interesting, I guess, from a machine learning perspective that even though you're using deep correspondence and kind of had, I don't know if that's the right term, but like some kind of ground truth of like at least the locations of these forms. And obviously they look different than in production or in prediction time, but the model still gave you a low confidence score. I'm curious why that happened.
Yeah, so so specifically for like the correspondence matching and the layout stuff, we were so one of the big focuses too that we've been having is I think the term is calibrated confidence score. So instead of we want the confidence score to be meaningful, and so oftentimes you'll just see like, well, this was the max logit of whatever, and so this is we do a greedy selection of what the prediction should be, and this one was the highest probability or something like that. And so we've been focusing a lot on doing a calibrated confidence score and asking ourselves, what does confidence actually, like, what does the confidence score actually mean? And so, like, one of the things that came out of some of the retrospectives we've had is that we should stop using the term confidence score, and there should always be some sort of descriptor as to what the confidence score actually is. And so, because like we say confidence score, and then we ask our partners, we say, oh, well, this is what we predicted 90% confidence on this, and some of them interpret it as like, well, out of 100 characters, maybe 10 of them are wrong, or out of out of a prediction of some transcription, we're 90% sure that the whole thing is right and that it would need to be fixed at all. And so we've been thinking a lot about what confidence score actually means. And the confidence score for us is really important because we have multiple steps in our pipeline for processing the data. And so we don't want to just dump whatever the machine comes out to our users. We want the machine to be smart enough to say, this is what I think it is, and I'm not very sure about it. And so you should have a human check it. And so we use these calibrated confidence scores to then filter what should be funneled straight to our website or straight to vendors to check and see if it is actually correct or not. And so specifically with the layout model, like that was one of the things that we found that we needed to improve on is because we didn't fine tune it for the 1950s data, the confidence scores weren't as trustworthy or weren't as useful. And so we've found in this experience that these calibrated confidence scores, they should be more meaningful beyond just like choosing what your prediction is going to be. It should be indicative to your partners and allow them to make business decisions based off of it.
Yeah, no, that's super impressive. I mean, I think being able to like find that metric that explains how well the model is doing, I think that's hard in every task, but specifically in this one when there's so many different models involved, and it's not just like straight classification or something that's fairly easy to explain, or at least we have metrics that with a little bit of explanation could precision recall, these kind of F1, these kind of things are fairly understandable. And I'm curious, when we spoke, you mentioned you kind of had these two main tasks around like deep correspondence and then the OCR component, and I think a lot of people consider OCR like a solved problem, but I'm curious, I know you mentioned you tried a few things, you actually use different models for the same task, so I'm curious if you can share more about that.
Yeah, so processing speed was really important to us, and so we wanted to have great results, and we wanted it as fast as possible for a number of reasons, to get it out to our users, but then the faster we could generate results, the faster we could start verifying that the results are good or bad. And so so the census, I think that I can't remember, there have to be more than like 50 different fields, and so the different fields.
Yeah, sorry for stopping. How big is the data set? I'm curious.
So the data set that we processed ended up being about 6.6 million images. I think that there were about 171 million individuals that we extracted from it.
Wow.
And so for each of those individuals, I can't remember, maybe 50 or more than 80 different fields. So capturing things as diverse as like within like how much money did they make in the last month. So like really kind of weird things that you wouldn't necessarily to capture, but it was important at the time, I guess. And so yeah, so obviously there are some fields that are more important, like the name of the person is really important, the age of the person, like having those two fields work really well allows you to find people pretty easily. Like knowing yeah, the income of a person isn't that important for finding them, but it's interesting to have. And so we found that we could use simpler models on some of these simpler fields, like some of them were just checkboxes. And so that was essentially just like a classification model. It's like, is it checked? Is it not checked? But some of the more complex models, like the name field, we ended up having to do like a full encoder decoder transformer model to be able to read it. And so like that model architecture is obviously more expensive computationally, but that field is so important to us that we're willing to bite the cost of computation. And additionally, like building infrastructure so that we could do easy post-processing on a lot of these. So trying to bake in knowledge, like there's this huge instructions document that they gave to the enumerators who walked around and filled out this information. So trying to become familiar with that, and then using that information as a way to post-process the outputs. So if we knew a field was only supposed to be numeric, we limit the outputs there. And so yeah, there were a lot of different architectures that we tried. There are some people familiar, like in the handwriting recognition space. There was a paper that came in a little while ago called OrigamiNet, which was very influential for us too. That was a pure CNN method for doing multi-line reading, which was really interesting. But yeah, so OCR usually is off. I mean, the connotation of that is it's applied to machine printed text. Okay. And there's online handwriting recognition. So if you can capture like stroke and pixel position and timing and stuff like that, those are fairly well solved problems. The historical documents are quite difficult because they can often be quite degraded, and the handwriting can be. My handwriting is not as good as theirs was back then, and so we found that historical documents, it really is important to have customized models, especially when high accuracy is really important to you. And so, like for personal use, you could probably get away with OCR, and if there's some mistakes in it, it's usually you can forgive it. But again, if someone's paying you for it, they want something really high quality, and so we've found that. Building these specialized approaches to historical documents is what gets us there.
Awesome. Yeah, I want to follow up on that. But before I do, for those of you in the audience, if you have any questions for Stanley or myself or in general, feel free to drop them in the question section, or it's right next to the chat on the right. We'll keep going, and then we'll have at the end a dedicated session to talk about some of these questions. But if there's something relevant for the discussion now, I'm happy to pick it up. So yeah, I think Stanley mentioned something really interesting, which typically affects people maybe in production environments where like, inference time could matter. In your case, it sounds like it was more of like an offline inference job where you're trying to index things. And you had multiple models where you have this trade-off between kind of inference time versus, accuracy or some form of quality. So you mentioned on the kind of the high end for these fields that are super important to use like an encoder decoder methods. What was the range here? So for like things that are less important, maybe someone's salary last month, what other models have you used for this?
Yeah, so the other handwriting recognition model architectures that we were using. Yeah, so like the classic approach that a lot of OCR engines use and a lot of handwriting recognition models use are LSTMs. Or some variation of RNN. So that was one of the architectures that we used. We also found that we could use just a normal transformer encoder approach to doing the predictions. The full encoder decoder one is helpful, especially for fields if they start trying to fit multiple lines of text within a field. So like oftentimes like occupations will take up multiple lines within the single cell. And so like usually the way that like LSTM models and like just the encoder transformer model have difficulties with multi-line text because they essentially take each pixel column of the image and use that as a time step, and they'll make a prediction based off of that. And so if you have multiple lines of text, you would need to be able to predict multiple characters per column or per time step. And so the full encoder decoder paradigm gets away from that. So it can learn what features it should be extracting at different time points, and then theoretically it should be learning to read through one line and then go back and then read the next line. And so we found that model was really important for us. And then the name field, again, it was complex, and names can be, they can be quite unique and quite long. And so, we found that, again, having the full transformer encoder decoder, having the memory that can access the full image seemed to be important for extracting those names.
Awesome. No, it's super impressive. And curious, I know you mentioned you guys were on a tight timeline before this gets passed off to human annotators. How long did it take you from the moment you kind of got the data set till you had, I guess, the first version of it indexed?
So we were able to process it in about 9 days. And so that was a big difference. So when the 1940s census released 10 years ago, which was a smaller data set, it took Ancestry, I think, about 9 months using vendors to hand key it. And so this was, this was a big investment in a big area that we think that we can really serve users and create a cool experience for them.
That's amazing. So everything you shared with us about trying to figure, obviously you spend a lot of time in the data, the different fields and what they look like and how they impact the model quality, but kind of everything you were talking about, you guys did in 9 days. That's like competitive machine learning.
9 days. It was a very stressful, long 9 days, and so I was very glad when it was over. But it was a ton of fun. It was a very exciting experience where, we were, like I said, it was the night of when the data was getting released. We were pulling samples of the data and running them through our development environment to try to do hyperparameter tuning on it. And it was, we were all sitting in a conference room at 3 a.m. and people from the partner team would walk by and ask how everything was going, and we would just tell them it was going okay. Not sure if we were going to find a good set of hyperparameters, but luckily we were able to. And so, it was a really exciting experience.
Awesome. No, that's so impressive. I mean, just talking to you now, there's so much scope in what you guys built, and the fact that you've done all of it in 9 days. Obviously, there was some prep work, but the vast majority of the research and the model building and obviously getting the results happen in 9 days is super impressive. And just to maybe, I know the answer, but just to give a sense for those in the audience, how big is the machine learning team that you're working with?
So there are, our direct team, like the handwriting recognition group, there are 4 of us or 5 of us, right? Someone just came on this week, actually. So there are 5 of us. Within our data science group, I think that there are about 10 or 15 of us. And then there's the engineering group that we work with. So I think that's another, 5 or 8 people. And so, our direct team is the 4, now 5 of us. And then we've worked pretty closely with 3 of the engineers. And so that was, the group that did most of the data science work for this particular project.
So impressive. Yeah, like the fact, this sounds like a work for like a team of 30 or 40 people. So super impressive. And maybe to switch gears, we covered a little bit of some of the technical aspects, but obviously, in order to be successful in something like this, it's not just about the technical aspect or figuring out the right model or optimizing it. It's about the process, right? And I think, there's a lot of teams out there that take, months, if not years, to build something that works. And, obviously every data set, every problem is different. But I'm curious if you can share a little bit about what your team's process looked like, and maybe how it changed based on what you've seen in this sprint on the census data.
Yeah, so it's kind of related to this first question, what are some of the biggest challenges that we faced? I think that, as our data science group has grown and as it's matured, Projects were often tackled by a single person, so they would own it. They would write all the code for it, and the code wasn't necessarily shared with anybody else. So they were, they owned that project. One of the big changes for this 1950 census thing is that there were multiple people, so there were 4 of us working on this, and so if it's just you working on a project, it can be easy to track things, and really you probably think you're doing better than you actually are. You're probably not tracking everything as well as you think you are, and you're probably forgetting things. But we found, especially with multiple people working on the same project, that collaboration and transparency and reproducibility were super big things. And so the term we started using was doing good science, and so making sure that are the results that I'm generating comparable to what the other person is generating? And so if we're both trying to improve the model, can we actually even compare the results that we're getting? Can I, what are the other people doing? Is there, and constantly having to ask someone what experiments they're running, what hyperparameters they're using, what model architectures they're experimenting with. That's a really slow and cumbersome process. In Comet, we had a common workspace that we were logging all of our experiments to, and so we could see what the results were looking like for somebody else, and we could peek at their hyperparameters and see what they were doing to try to get it to work better. And so there was just way more collaboration. Additionally, a standardization in terms of how we report our results, and how we're all logging things the same way, instead of some people are dumping everything to a text file and then bringing it into an Excel spreadsheet or a Google sheet or something like that, and then making charts or something. That's not scalable when you have really large and high risk types of projects. And so you want something that's automated, something that's standardized. This infrastructure thing is so key, where like I said earlier, like a lot of times the focus is like the actual model architecture and like innovations there, but having a cool model architecture, that doesn't make it easier to maintain. That doesn't make it easier to know what you need to tweak to get it to work well. It doesn't help you report to your partners how it's doing. And so the amount of standardization that we've been able to do just because we have this infrastructure tool that Comet provides has been really great for us. And there are other parts of it that we haven't utilized yet, but we're really excited for. So like just being, and you mentioned this like in the survey results, but like how do we version certain model weights that were trained on certain data sets? Maybe we've augmented the data set with some new labeled data, and now we want to retain the old model. And we found that just keeping the model weights in an S3 bucket that you can then overwrite, and you don't know where the old weights went. That's not a good way to version your models. And so we're really excited for that. Also, another thing that we're really excited for, like the artifact store, being able to version our data in the first place, is something that we're amassing so much labeled data. Now it's becoming difficult to track all of it. And so, I was talking to someone the other day, and they said that they found a data set sitting in an S3 bucket, and they're not sure where it came from, but they started using it. And it's like, well,
and it happened to be the same data set as the test set, so results.
Hopefully that wasn't the case, but
yeah, I think that happens all the time. I mean, S3 is a great object store, but if you don't know the version of the data set, you don't know which code, which pipeline, which experiment generated it, you don't know which model consumes it. Like, if you don't have all that information, it's like really, really hard, because and these problems have been going on for years. When I was at Google and I was working, and I mentioned, on hate speech detection and YouTube comments. And one of the things when I picked up this project was my task was to try to beat the production model. And the first thing you ask is like, okay, what's running in production? That's the first thing. And to my surprise, people shared slides, Excel sheets with me. So it was super hard to reproduce. But then the second one is like, what data is this training, and where's the data? And then at Google, it's not S3, they have something called SS tables, but like they shared this, and I was like, okay, like there's like different subset here, feature, what are we using, what's working, what's not working, do I know I'm not kind of mixing up test and train here? Super, super painful. But yeah, I mean, I think well from here from some of our customers that once you have that lineage, you know, okay, this is the data set it was trained on, this is the code that generated it, this is where it's stored, this is the multiple versions of it, this is the experiment that consumed it, and this is the model weights coming out from that experiment. Just gives you a lot more confidence in kind of per your comment on doing good science.
Yeah. Yeah, it's yeah, emphasizing the science part of data science is something that's we found is important. So
Awesome.
yeah.
Cool, Stan. So I think thank you so much, by the way, for answering. I know we might have some questions from the audience that I'd like to cover, but before we kind of move to the next section, one question I like to ask every data scientist I speak to is, like, with unlimited budget of GPUs, unlimited data, unlimited everything, which problem would you work on? Or what model would you build?
Yeah, so I mean, the reason I love computers is the idea of automating the mundane stuff in our lives, and making it so that people are free to do creative stuff. And so I think that's one of the reasons I really like this historical document, like automated document processing space. Like, it's just something that people shouldn't have to do. We shouldn't have to sit here and read to try to extract that information. And so, like, something I would love to do is you know, I think we've all seen like those reinforcement learning, like playing Atari or AlphaGo and stuff like that. And it's just like, man, that stuff is so cool. And like, I would love to be able to build an AI that, you know, is looking at documents and being able to automatically extract the information, tell you what information is on it, try to link it to other documents that might exist somewhere else that it's seen before, or, you know, somehow be able to link it to like pictures of the person, and it knows a certain thing about them because of things that were indicative within the historical document, based off of, I don't know, like contextual clues or something. And so like a lot of that logic, well, all that logic we have to bake in manually, and we have to think explicitly about, but for it to be able to reason about documents and then get it so that people aren't sitting here like scrolling through a bunch, like a huge pile of images just trying to find a relative's name, but they're able to construct this life story based off of all this information that was extracted automatically and just being fed to them.
Awesome. No, I mean, I think you definitely, if you've done this in 9 days, I don't know if you need unlimited budget. You probably get it done in 2 weeks in this case, but you totally see the value of it. So thanks for answering. So kind of switching gears, if you're in the audience and you have questions for Stanley, now's definitely the time to drop them in the question section. I'll kick it off with some of the questions. So we have a question from, I hope I'm pronouncing the name right, Ade or Ade. I'm sorry if I'm mispronouncing it. And the question is for Stanley. Stanley, you mentioned the ability to get pretty speedy feedback from your end users about model performance. Could you say more about how this was engineered? What constituted feedback in this instance? And what was your process for incorporating this into your model experimentation, hyperparameter tuning, etc.?
Yeah, so there was so we're integrating into a legacy system where the original pipeline, it was all built around humans doing these things. And so like they would have one vendor transcribe, and then they'd have one vendor check to make sure that the transcriptions are correct. And so there's this large network of, or this large pipeline of doing manual QA that was kind of built out already. And so they have contractors that they have longstanding relationships that are used to, you know, they have these pages long documents that indicate how they're supposed to evaluate certain things, and they do trainings with them. And so that is a method that they use to provide feedback to us in a quick manner. And so when data hit Thursday night and we were processing stuff, as soon as it would go through the data science pipeline, it was being moved off to these QA pipelines. And so they have, you know, tooling to be able to visualize and see how well things are actually performing. And this is something that they do like in normal projects as well, but they just scaled it up quite a bit to be able to process this volume of data quickly. And so we were getting periodic results from our partner teams saying how the vendors thought it was performing. And so I remember like we were about a day into processing, and we found that, you know, some of the results were pretty good, but there were a lot of, you know, certain census form types that we were failing on. And that came back via that vendor network. And so being able to talk with, I mean, a lot of this, this infrastructure was built around like having good communication and having daily stand-up meetings with our partner meetings, so we weren't siloed with them. And so like it's building those relationships so you're not siloed can be really difficult, especially in your day-to-day work. And so I think one of the things that, so specifically about Comet that we've really liked is that it allows for an amount of transparency. And we've also experimented with using, I think, the Gradio panels in Comet, so that our users can they can submit inputs, and they can, I mean, not that they would ever distrust us or that we were fudging our results, but they can input things and see what the outputs look like. That just adds another level of transparency that they can look at. And so that is one of the big pushes we're making, is trying to I hesitate to use the word like commoditize or commodify, but democratize the models that we're using, so it's not sitting behind this data science firewall that people can't access and stuff like that. And so like just some person, we have a new collection coming in and we're not sure how it's going to perform, they can just send it through the pipeline and see what the results look like themselves, and if they notice something, they can give us feedback. But yeah, a lot of times, like, yeah, it's been where the model itself is a black box. Partner teams don't get to have input on how it actually works. But that's a paradigm that we're trying to change with, you know, the infrastructure and tooling that we're using, but also the types of model architectures that we're using. So like the deep correspondence, where the partner teams, they chose what the exemplar images were supposed to be and not us, because they felt like that those were the best things and those were the best, you know, landmarks that indicate differences. And so I have no idea if I'm answering the question. I feel like
I think 100%. The first part, 100%. Kind of maybe let's dive in a little bit in the second part. So I think you talk about how do you get this feedback from the partners team. What was your process for incorporating it back into like the modeling project, or like, you know, trying different things, hyperparameters, models, architectures, data set changes? What does that look like?
Yeah, so we would get the feedback. So specifically with the 1950 census, it was a day in and we got that feedback that we were having poor performance in certain areas. And so all the data scientists, we had standardized our code, so other people, not just the one person who had developed it, could use it. And so we were all just experimenting with different hyperparameters. We had also built it so that, you know, we could log to Comet if our partner teams wanted to be able to see that information. But that night, it was a big scramble. That was I don't know if it's exactly representative of what the process would normally be. In some of the other projects that we've had, the process for us updating our models, it usually comes down to like there needs to be an evaluation of how does data science best use their time. So maybe it's not worth us updating the model because we can fix it easily in some kind of post-processing thing, or the vendors, we can get them to fix something really easily. Like having them rekey someone's name is really expensive, but having them fix like the line number, it's just a sequence number of where they were on the page, like that's really easy and cheap for them to do. So being able to identify and make business decisions that way as to what actually is causing a problem. And so, evaluating the feasibility and the cost associated with building a solution. And usually, so with the models that we've built, we've tried to remove every single magic number that exists in our code, and we have it's all sitting in config files, and we've tried to modularize everything. And so modification of the models is quite cheap now, and experimenting with new hyperparameters is easy. And so we're also standardizing how we do our QA, and so that we can do it in an automated fashion. And so it's, if you ask us the same question in like a year, it's probably gonna be a totally different process. the data science at Ancestry, we're evolving very rapidly, and like when I started just in 2019, things are totally different now, and so it's yeah, it's really cool to see the changes that have come, and especially highlights the need for like infrastructure, which is not something that I thought much about at school. So
Yeah, and you shouldn't think about it in school, right? But you know, for a lot of people who go from like academia to industry, like it's just like a shock of like how hard these things are. And in some ways, like how little like the specific architecture you have, how little the impact is, where really like you can make huge changes by investing in infrastructure, by things like post-processing, which might not be like sexy as like coming up with a new architecture, but it works really well. So I think we have time for one last question before we have to wrap up. I think it's in a sense similar to the last one. So, but maybe let me know if you want to add anything to that. So this is a question from Vinette, who asked, how did you do evaluation given labels weren't given? So I think you touched on it earlier, but would love to hear your response to that.
yeah, so our partner teams, they have a standard process for sampling from data sets and then sending them through to their vendors to manually check. It's a process that we're actually trying to get away from, because having a human in the loop, it can cause errors, especially when we're using vendors that English might not be their first language or something like that. So it's when we have like an English specific data set that we're working with, especially like I have a hard time reading cursive, and I grew up here,
Yeah.
and so so that can be difficult. But that was the way that we were evaluating things, and so there were specific criteria that we could use to see how well, like the step we call is layout detection, so identifying where the form is in the image and making sure that we're extracting each of the columns correctly. So there are certain types of specific types of errors that we had identified, and so a person would check those. And then we have the vendors again look at specific fields and see if a particular character or a particular transcription is correct or not. So it's an all or nothing check, and we found that we were actually getting really great results. And we found that we don't actually need perfect results too, because search will compensate for a lot of the mistranscriptions. And we're actually experimenting with something right now where we actually try to use the I think this is another struggle that we've had, is where each model lives kind of in a vacuum and it's unaware of what the other model is doing. And so we're experimenting with using the handwriting recognition to verify that we actually extracted the layout correctly. And so if we are extracting the data on the form in the correct places, we should know where certain things are. Like each of the rows of the census form that we extract, like the first one should start with the number 1 within like that line number field. And so we can use the handwriting recognition to read that. And if it doesn't match up, then we know we found an error. And so we've been, again, it's like automating mundane tasks and trying to get humans to do more the difficult creative type tasks. And so can we use our models to fix that stuff? And so it's definitely an area that we're exploring and trying to develop. But specifically for the 1950 census, it was a lot of manual checking that luckily didn't come out of our budget. So it's
Awesome. Yeah, I mean, I think one of the things, among a lot of others, one of the things that's most impressive to me is, and I think maybe, speaking about academia versus industry, is like how deep you went in the data, and not just focus on architectures and models and transformers and metrics, but really like you obviously understand the data set like extremely well, which sounds like helps you come up with different ideas to build better models and overall improve this task. But unfortunately we have to wrap up. I feel like we could keep going for another hour easily. But Stanley, it was an absolute pleasure to have you here today. Thank you so much for joining us and sharing some of your learnings and success with our audience. Really appreciate it. Thanks everyone in the audience for joining us. Like I mentioned, if you want to see the survey results, it's available on the handout section. And then if you're watching this async on YouTube or through another system, you can always go to our website, comment.ml, and you should have access to the server there. Thank you so much for joining us today, and I hope everyone has a great rest of the week.